work and energy. In this chapter, we just want to make the understanding about work and the relation of the work in the physics to the energy. Then the first of all, we talk about the definition of the work. And then later, let's talk about the work energy theorem. So this theorem is going to be the link between the work and the energy that we just want to use. And then we just define the kinetic energy. And then later on, we talk about the work done by the typical forces. For example, the work done by the weight and the work done by the resulting force of the spring. And then we're gonna introduce the potential energy of the weight and the resulting force of the spring as well. We talk about the the conservative and the non-conservative forces, and then the conservation of the energy. And then we can point our interest to the conservative forces. Okay, so we're gonna have the link between the conservative force and the potential energy here. And then finally we talk about the power. So now, the first of all, what is the work in the physics, right? In the physics, the work is a process of the energy transfer to the motion of an object via the application of the force. So in this case, the object can gain the energy or can lose the energy depending on the type of the force we are considering. So let's consider this one. If we have a force F, okay, making some angle theta to the horizontal axis, and then apply to the object. So in this case, you can see that, okay, if the object just move to this position, okay, if the object just move to this position with okay, so if the object just move to this position with the displacement equal to let's say delta x, okay, let's say equal to the delta x here. This is the displacement the object can move. So then the question is, which component of the force will make the object move to this horizontal? Okay, which component of the force will make the object move to this horizontal? So let's see. If we break this force into the two components, the first one is the horizontal one and the second one is the vertical one. So this component is equal to the F and then times the cosine theta, right? And then this component is equal to F and then times the sine theta. So now you can see that the one that make the object, right, just move to the horizontal axis here is the horizontal component of the force. Okay, so it's going to be this one. Okay, so let's just ignore here. Okay, let's ignore here. Okay, so let's say that this one is going to be equal to the F parallel. Okay, equal to the F parallel. So where the F parallel is is the component of the force F, which is parallel to the displacement delta x. Okay, delta x. Then we can see that the work done on a body by the force F is, okay, when we talk about the work done, so we should talk about the work done on which one, okay, on which one and by which force. Okay, we talk about the work done, you have to always think that the work done on which one and by which force. Okay, we use the symbol of the work done to be W. It's going to be equal to the F parallel. Okay, so this component, and then times the displacement delta x. Okay, the F parallel, and then times the displacement delta x here equal to, okay, if we sub the F cosine theta into this equation, we can get it to be the F and then times delta x and then times the cosine theta. So don't forget that the theta here is with the angle between the F and then the displacement. Okay, let me take a note here. Let's see. Okay, if this one is the first F, and then if this is the delta x, okay, this is the delta x, so this is the theta, the angle between the F and delta x here. Okay, one more thing, you can see that the first F here is a vector quantity and delta x is a vector quantity as well, right? So the first F and delta x are the vectors quantities. So we have the two vectors multiply to each other and then get a scalar quantity, because the work done doesn't have the direction, it has only the magnitude. Okay, so this is the scalar quantity. So it means that we need to use the dot product. Okay, we need to use dot product or the scalar product in this case. Then it's gonna be equal to the F, okay, the vector F, and then dot. Okay, for the displacement, right? Okay, in the general case for the three-dimensional motion, let's say that we use the delta vector r, right? Delta vector r here for the displacement. Okay, so this can be the definition of the work done. What is the unit of the work done? Okay, what is the unit of the work done? You can guess that the unit of the work done here is, okay, the first F, right, is Newton, and unit of the displacement delta x is meter. But also we can use the unit as the joules, Joule, the unit of the energy, as you have seen many times already, and the capital J, right, the capital J here. Okay, one thing that you can see from this equation is that, okay, we can have, okay, in the case, so let's consider for each case, when the F and the displacement have the same direction, okay, when the F and the displacement, let's say delta r, has the same direction. So in this case, it means that the theta, right, the angle between the first F and the displacement must be equal to the 0 degree. Okay, must be equal to the 0 degree. In this case, okay, the cosine theta, theta equal to 0, cosine 0 equal to 1, right? It means that the work done must be positive. Okay, the work done must be positive. That's the first case. But then if the first F and the displacement just point to the opposite direction, okay, so let's say this is the delta r. If the first F and the displacement just point to the opposite direction, it means that the angle between these two, right, so this one, this angle must be equal to the 100 and the 80 degree, and this can be the theta. Theta equal to the 100 and the 80 degree. So in this case, the cosine of the 100 and the 80 degree equal to the -1. So it means that the work done must be negative, right? Okay, the work done must be negative. Okay, the last one, if the force F is perpendicular to the displacement in this case. Okay, if the force F is perpendicular to the displacement, then in this case we can get that the theta, right, the angle between the force F and the displacement equal to the 90 degree. Okay, then cosine 90 equal to the 0, then we have the work done equal to the 0 as well. So what is the meaning of the work done to be positive, negative, or the 0, right? So later I'm trying to link, okay, so later I will try to link the work done to the change in the kinetic energy. Okay, but then here let's talk first. If the work done is positive, it means that the object, right, the object will gain the energy. Okay, the object will gain the energy. Then again, later I will talk which type of the energy that the object gains. Okay, if the work done is negative, it means that the object will lose the energy. Okay, if the work done is equal to the 0, okay, it means that there's no energy transfer. Oops, there's no energy transfer from or to the object. Okay, from or to from, let me write here, from or to the object. So it means that the energy of the object doesn't change. Okay, so this is what we get, right, from the equation. So let's look at these examples. So let me take a copy first. Okay, examples. A block of the mass 80 kilogram, right, just slides on an incline with distance 12 meter. Okay, so this means the displacement the object can move, but I mean right now we don't know yet. Wait. Okay, so right now we don't know yet that the object will move up or move down, right? Because the question just tells us only the slide or the incline. We don't know that it's going to go upwards or the downward direction. The coefficient of the kinetic friction between the block and the incline is the mu k. Okay, so answer the following questions. Okay, so we have this picture already. Now for the part A. Okay, for the part A, draw the free body diagram of the block. Okay, so let's draw the free body diagram of the block. So now we have the force F already, right, equal to the 600 Newton. So what else do we have? We must have the weight. Okay, we must have the weight here. Let's say that the weight here equal to the m times the g. The weight here equal to the m times the g, right? And then what else? We have the normal force. Normal force just point to this direction. Okay, let's say we have the normal force equal to the small n, right? And then we must have the kinetic friction, okay, because the object is moving along the incline. We must have the kinetic friction. Then we don't know yet that, I mean, the friction will go to the downward direction or to the upward direction. So we still don't know, okay? Then we need to check. We need to check that, okay, we have this F, right? If we break the F into the horizontal axis here, and also if we break the mg to the horizontal axis here as well, so which one will we win? Okay, which one will win? Then we need to compare. Then okay, here let's guess that, okay, just guess that the friction just point to this direction. Okay, let's guess the friction just point to this direction. This is the Fk, the kinetic friction. Okay, but then again, it may be wrong, right? So if it's wrong, then we can just change this to this direction. So that's fine. Okay, now for the part B. Right, so this is what we want. Okay, will the block slide up or down the incline? So as I just mentioned, okay, then we need to check. Let me just make it smaller. Okay, so how, right? Then we need to break the force, okay, the F, this F, right, and then the mg to be the horizontal and vertical to the incline. Then let's consider the mg first. Okay, so we have this component of the mg. So this can be equal to the mg and then times the cosine 60 degree, right? Okay, because this angle equal to 60 degree. And then this component is the mg and then times the sine 60 degree. So now is the turn of this force F, right? Then we can just break the force F into, let's say this one. This one is the F and then cosine 37 degree, right? And then this component is going to be equal to the F and then times the sine 37 degree as well. Okay, so now let's set up the axis. Okay, let's set up the axis here. As usual, we say that vertical to the incline, right, is going to be the y-axis, and horizontal to the incline is going to be the x-axis here. Yep, something like this. Okay, so this could be y-axis and this going to be the horizontal axis, right? Let's consider the y-axis first. Oops. Because the block it just slide up or down the incline, right? It's not moving along the y-axis. It means that the net force on the y-axis must be equal to 0. Then we can see that we have the normal force and the F sine 37 degree, right? Just point to the upward direction here. Okay, just point to the positive y-axis. And then the mg cosine 60 just point to the negative y-axis. Then in this case, we can get that the normal force and then plus the F times the sine 37 degree, okay, must be equal to the mg times the cosine 60 degree. Or we can see that the normal force, right, normal force here must be equal to the mg cosine 60 degree, right, and then minus the F times the sine 37 degree. So let's sub the numbers into the equations. The M, the mass of the block is the 80 kilogram, right? Okay, just put the 80 here. And the G is the 9.81. We have the cosine 60 degree and minus the F is the 600 Newton. And then times the sine 37 degree. Okay, after using the calculator, you can get the number to be 31 Newton. So this can be the normal force that we can get. Okay, the 31 Newton. Okay, so now let's consider the x-axis. Okay, so then again, right, just as I mentioned before, we need to compare between the f cosine 37 degree and the mg sine 60 degree and see which one we have the larger amplitude. The larger magnitude. Okay, so let's consider this one, the f cosine 37 degree equal to, so the first f equal to the 600 and then times the cosine 37, right? In this case, it's going to be equal to the 4x0 Newton. This is the f cos 37. Now this one, the mg sine 60. Okay, we have the mass equal to the 80 times the g 9.81 and then times the sine of the 60 degree. In this case, it's going to be equal to 6x0 Newton. Okay, 6x0 Newton. So now you can see that the mg sine 60 degree, right, which is equal to this value, is greater than the f cosine 37 degree. Okay, so it means that this downward force is larger than the upward force here. Then it means that the block will just slice down the incline. Okay, the block will just slice down the incline, and that's it. So in this picture, I need to change. Okay, I need to change. So let's say that the FK should point to the opposite direction here. Okay, this will be the FK, just point to the opposite direction. Okay, so the mg sine 60 is the 680 Newton, and the f cosine 37 degree is 480 Newton, and then we have the Fk, right, the kinetic friction force. Okay, so just compute the Fk. I mean, in the case that we need to use it in the future, right? Okay, so the Fk is equal to the mu k and then times normal force. Mu k is what? Mu k is equal to the 0.4, right? Mu k is the 0.40, and then normal force is equal to the 31 Newton. Then we can get the mu k to be 13 Newton. Okay, so we're going to use the Fk in the future. So let's just calculate first. Good. So now for the part C. Okay, part C. Calculate the work done by the weight, right? Okay, just calculate the work done by the weight. Okay, let me use a symbol as the WG. Okay, the work done by gravity or the work done by the weight, it's just the same thing. Okay, so now let's consider these figures again. For the weight, right, the mg, we have the two components, the mg sine 60 degree and the mg cosine 60 degree, right? But now you can see that this is the one which is parallel to the displacement because the object is just slowing down. Okay, let me just, okay, yeah, because the object is just slowing down the incline, right? So this one must have the same direction as the displacement, and this one is not. This one is perpendicular to the displacement, so the work done by this component must be equal to the 0, right? Then for this case, okay, for the mg sine 60, we can get the work done to be the mg sine 60 degree, right? So this is the force, and then times the displacement, let's say delta x, okay, and then the angles between the mg sine 60 and the displacement here must be equal to 0 degree, right? 0 degree. So in this case, equal to 1. So now plug in the number. Mg sine 60 equal to what? Mg sine 60 equal to 680 Newton, right? The 680 Newton, and then times the displacement delta x, 12 meter, okay, 12 meter. So then here, we can get the mg to be, we can get the work done by the gravity or the work done by the weight, right, to be equal to 4.1 times 10 to the 4 joules. Okay, 4.1 times 10 to the 4 joules. This will be the work done by the weight. Now for the part D, we need to calculate the work done by the force F. Okay, the work done by the force F. So the work done by this one. Then again, right, you can see that the force F here, we can separate into the two components, the F sine 37 degree and the F cosine 37 degree. So this one is perpendicular to the displacement, so the work done by this one equal to the 0. So let's just ignore this. But now here, right, the F cosine 37 degree, the object just moved down the incline, but now this force just opposite to the displacement, right? It means that the angle between the displacement and this component of the force equal to the 180 degree. Okay, then we can get that the work done by the force F equal to the F what? The F cosine 37 degree, and then times the displacement equal to delta x, and then times the cosine 180 degree. So we know that the cosine 180 degree equal to the -1. Then we can get the work done by the force F to be minus, right? Minus for this one. And the force F, the F cosine 37 degree equal to what? I don't know, we haven't found yet, right? The 600, and then cosine 37 degree, and then times delta x, which is equal to the 12. So in this case, it's going to be equal to minus 0.58, okay, times 10 to the 4 joules. Actually, let me just change this answer to be the 41. Okay, 41 times 10 to the 3, and let me just change this answer to be the 5.8 times 10 to the 3. Okay, so this is just look nicer. For the part E, okay, so let's calculate the work done by the Fk by the kinetic friction. Okay, so just the same, right, as this component, because the Fk is opposite to the displacement, the work done must be negative, and the angle between the displacement and the force must be equal to the 100 and the 80 degree, right? So then here we have that the work done by the friction, right? So let's get the Wf, the small f here, equal to the Fk, and then times delta x, and then times the cosine 100 and the 80 degree. So which we know the answer already for this one, equal to the -1. Okay. So now let's just plug in the Fk into the equation. The Fk is what? Fk is the 13 Newton. So we have negative of the 13, and then times 12, right, for the delta x to be 12. Then equal to minus 0.15 times 10 to the 3 joules. Okay, so this can be the the work done by the kinetic friction. So in this case, you can see that the work done by gravity, right, will give the energy to the block, but the work done by the force F and the work done by the friction, right, will make the block lose the energy as moving. Okay, now for the part F. Okay, so this means the work done by the resultant force. Okay, determine the work done by the resultant force here. Actually, we have the two approach that we can do, right? We can just find the resultant force first and then compute the work done by the resultant force, or we just sum all the work done by everything here. Okay, just be the same. Actually, wait, I forgot something. I forgot another force, sorry, for the part F. Yep, right, I forgot another force. The work done by normal force. Sorry. Okay, for the part F, just calculate the work done by normal force N, right? The work done by normal force N. Okay, so this is easy because what? Because you can see that the normal force, right, is just perpendicular to the displacement. Okay, so it means that the angle between the normal force and the displacement equal to the 90 degree, right? So we can say that the normal force is perpendicular to the displacement. So it means that the angle is just 90 degree. Okay, then you can see that the work done by the normal force must be equal to the 0. Okay, and that's it, because the normal force will not contribute any energy to the motion of the object, right? The object will not gain or lose energy by the normal force here. So the work done by normal force must be equal to the 0 in this case. Okay, so now okay, F and G, right? So now for the part G. So we need to determine the work done by the resultant force. As I mentioned before, we can have the two approaches that we can solve for this one, right? The first one is we just find the resultant force and then find the work done by the resultant force. That's quite simple. Or the second approach is we just combine the work done by all the forces acting on the object, and that's it, right? Then we should get the same answers as well. Then let's do the approach one. Okay, let's do the approach one. You can see that the net force, all the resultant force, right, is what? So we have the mg sine going down, the f cos and the fk just in the upward direction, right? And this one doesn't contribute for the net force here. Then we have net force equal to the mg times the sine 60 degree, right? And then minus the f times the cosine 37 degree, and then minus the kinetic friction, the fk. Equal to, okay, equal to mg sine 60 equal to the 600 and the 80 Newton, and then minus the f cosine 37, right, equal to the 4x0, okay, and then minus the fk is what? The 13 Newton, okay, just equal to the 13 Newton. Then in this case, we can get the work done by the net force equal to one 188 Newton. Okay, but if we just take only for the two significant figures, right, it's going to be equal to 1190 Newton for the two significant figures here. Then we can get that the work done by net force, right, is going to be equal to the net force and then times the displacement, okay, and then times the cosine 0 degree, right, because in this case the net force just parallel in the same direction as the displacement. Then we have work done by net force equal to the 190 and then times 12 and cosine 0 equal to 1. So the answer is 2300 joules. Okay, 2300 joules. So now let's find for the method 2. Okay, so let's compute the work done by the resultant force for the method 2. So as I mentioned before, right, the work done by this resultant force, it must be equal to the work done by all the forces together. We have the work done by the gravity, right, and we have the work done by the force F, and the work done by the friction, and then the work done by the normal force, which is equal to, okay, so the work done by the gravity equal to this value, minus the work done by the applied force F equal to this one, and then minus the work done by the friction, right, equal to this one, and then plus 0. Okay, then we expect to have the same answer to be the 2300 joules.